the 4 astronauts on Artemis II who've just provided us an update on the 4th day of their moon mission.
Now, these are the first of many incredible images of the moon, and we'll continue to release them as they become available. My understanding from just a few minutes ago is that they captured over 175 gigabytes of imagery from the lunar pass alone just yesterday.
Something was detected during Artemis II. And according to every instrument, every map, and every data set built over 53 years of lunar science, it should not exist. The crew saw it with their own eyes. They cross-checked it with each other. They logged it in real time. And when scientists on the ground tried to match what the astronauts described against 5 decades of satellite data, they came up empty.
Last night, we did have our first view of the moon far side, and it was just absolutely spectacular. I think that one of the interesting things that happens when you look at a moon that inherently just looks different.
Not because we missed it, but because the system we built to study the moon was never capable of seeing it at all. The mission that changed everything. On April 1st, 2026, the Space Launch System lifted off from Launch Pad 39B at Kennedy Space Center at 6:35 p.m. Eastern Time. Inside the Orion capsule, named Integrity, were 4 astronauts: Commander Reed Wiseman, pilot Victor Glover, mission specialist Christina Koch, and Jeremy Hansen from the Canadian Space Agency. This was Artemis II, not a landing mission, but a crewed loop around the moon, designed to validate every system before Artemis III attempts an actual landing. The trajectory was a free return path, shaped entirely by gravity, carrying the spacecraft around the far side and back to Earth, without requiring major additional propulsion. Clean, efficient, and precisely planned.
The darker parts just aren't quite in the right place, and something about you senses that is not the moon that I'm used to seeing. And sure enough, we got out our lunar targeting information, and we matched up, and we're like, yeah, that is the dark side.
What it was not planned for was what the crew was about to see. The darker parts just weren't quite in the right place, and something about it told them, this is not the moon I'm used to seeing. So they pulled out their lunar targeting information, matched it up, and realized that is the far side. For more than 5 decades, since Apollo 17 in December 1972, no human being had traveled to the moon. Everything we knew about the lunar surface in that time came from instruments orbiting hundreds of kilometers above it. NASA's Lunar Reconnaissance Orbiter, launched in 2009, mapped the entire surface in high resolution. China's Chang'e missions and Japan's Kaguya spacecraft added spectral data, revealing chemical composition through reflected light. These systems operated continuously, sending back terabytes of information, but all of them share a limitation that is easy to underestimate. They are programmed before launch. They collect light within specific spectral ranges chosen in advance, built on existing knowledge and existing expectations. They observe from fixed altitudes and fixed angles.
I will just say a couple of things about yesterday's operations. Really provided a great opportunity to test how our flight operations teams and our science teams are working together in real time with the crews at the moon.
Unable to adapt in real time as lighting conditions change. When something falls outside those preset ranges, it doesn't register as an anomaly. It doesn't register at all. The human eye is different. It adapts instantly. It detects subtle color variation under low illumination in ways standard digital sensors struggle to replicate. Yesterday's operations provided a great opportunity to test how our flight operations teams and our science team are working together in real time with the crew at the moon, especially when sunlight strikes at a shallow angle near the horizon, casting long shadows that reveal surface detail invisible from directly above. A trained human observer in the right position can notice something that no algorithm would flag, because no algorithm was written to look for it. That is exactly the light Orion encountered as it passed over the far side of the moon on April 6, 2026. Low sun, long shadows, lateral movement across terrain that no human had looked at from this altitude and angle since Apollo. And during 7 hours, at roughly 115 kilometers above the surface, 4 human eyes were about to test 5 decades of satellite data from the outside. For the very first time, the data didn't pass. Farther than anyone has ever been at 1:57 p.m. on April 6th, Jeremy Hansen read aloud a number from the control panel. 252,756 miles from Earth. In that moment, Artemis II officially surpassed the farthest distance any human being had ever traveled, a record previously held by Apollo 13, which reached 248,655 miles in April 1970. But here's what most people don't know about that Apollo 13 record. It was never an observation. On April 13, 1970, an oxygen tank in the service module exploded.
That is something we have never seen before. We must be, no kidding, like Reed said, somewhere between the Earth and the Moon, getting a view from a different place.
Forcing the crew to abandon their original flight plan and use the lunar module Aquarius as a lifeboat. From that moment forward, every decision was about survival. No one was watching the moon. No one was taking notes. The 248,655-mile figure is a record of distance, not a record of human eyes on the lunar surface. Artemis II was different. All systems were functional. The crew had a defined task: work through 35 pre-selected observation targets as Orion passed over the far side. Record what you see, log the time and coordinates, cross-check with each other. That is something we have never seen before. No kidding. Like Reed said, somewhere between the Earth and the Moon, getting a view from a different place that transforms 252,756 miles into something far more significant than a number in a record book. It was the first time in history that humans reached this far with the ability to actually watch, and with nothing between them and the surface but 115 kilometers of vacuum. Think about what that actually means. The Lunar Reconnaissance Orbiter operates at an average altitude of about 50 kilometers, with cameras optimized for specific lighting conditions and imaging cycles designed for systematic global coverage. China's Chang'e 4 lander provides surface data from a single fixed location on the far side. Japan's Kaguya mission ended in 2009. None of those systems ever collected data from Orion's exact vantage point at that altitude, under that angle of light, moving laterally across terrain where shadows stretch long and sharp, and the surface reveals details that simply don't show from directly above.
We saw some amazing sights, the Earth setting and rising, the sun going behind the moon and then coming back out, and all of the fantastic cosmic phenomenon.
There is no reference data set for the far side under those exact conditions. That alone should give you pause. But the real problem begins when the crew's descriptions don't match the existing data at all, even after accounting for every difference in angle and illumination. If this is the first time you're hearing what the crew actually described during that pass, that's exactly why this channel exists. Hit subscribe, because what comes next is the part NASA hasn't officially explained yet. Colors that shouldn't be there. The crew worked through their target list methodically. Impact basins, crater rims, geologically significant regions, 35 pre-selected locations, each with coordinates logged, each with a spectral reference from the existing data. At each one, they observed, recorded, and captured imagery. They saw amazing sights, the Earth setting and rising, the sun going behind the moon and then coming back out, and all of the fantastic cosmic phenomena. Standard procedure, carefully planned, carefully executed. The idea was that what they saw would roughly correspond to what the instruments had already told us was there. That assumption lasted about 30 minutes. Christina Koch was at the window when Orion passed over Mare Orientale, a massive impact basin, roughly 930 kilometers in diameter, on the western far side. One of the most well-preserved structures on the entire moon. She had reviewed the orbital imagery before the mission. She knew the reference data by heart. She noted that the ejecta along the rim appeared almost silver in tone, sharper and more defined than in any orbital image she had studied. Low-angle light enhances contrast. That much was expected. What wasn't expected were the color variations she logged along the rim's edge. Subtle gradients, shifting slowly across the ejecta field in ways that didn't correspond to any known mineral pattern in the spectral maps. She documented each one. She did not have an explanation for any of them. Here's where it gets uncomfortable. Victor Glover had his face close to the window when Orion crossed the South Pole Aitken
We hit
Basin.
close to 4Gs a couple times on the reentry profile. You saw the plasma coming. For me, it started high and started coming down. It was red, but then it was green and bluish, and it was bright, and it was like somebody was welding outside the capsule.
The largest known impact structure in the solar system, roughly 2,500 kilometers across and up to 8 kilometers deep. He had studied this basin. He knew the spectral data. On the basin floor, he saw a faint hue that read almost green, not gray, not white. Something he had never seen on the near side of the moon and had never seen in any image of this region. He didn't call it out immediately. He looked for a moment, checked his reference materials, looked again. Then he said it out loud and turned to Coke. "Tell me what color that looks like to you." She looked. She confirmed it. Green. Earlier Apollo-era imagery contained faint hints of unusual coloration in this region, but the resolution was never sufficient for confirmation. The Lunar Reconnaissance Orbiter later detected uneven mineral signals across the basin floor, inconsistencies that were logged and largely set aside. Nothing in any existing data set corresponded to what Glover and Koch were looking at in real time. Nobody caught it for 53 years. They hit close to 4Gs a couple of times on the re-entry profile. You saw the plasma coming off the capsule. It started high and started coming down. It was red, but then it was green and bluish, and it was bright. It was like somebody was welding outside the capsule. Jeremy Hansen guided the crew toward the von Karman Highlands, the ancient geological region where China's Chang'e 4 mission landed in 2019. One of the most extensively studied areas on the entire far side. The Yutu-2 rover had driven across this ground. The LRO had imaged it dozens of times. There was more data for this location than almost any other point on the far side. As Orion passed overhead, all 4 crew members described swirls of olive and pale green across the gray-white regolith. None of that data showed those colors, not even close. In Houston, flight controllers pulled up spectral maps in real time and ran comparison after comparison. No match. There are reasonable explanations worth considering. Lighting angle alters perceived color.
And the mission isn't over yet. We do continue to learn from how our spacecraft and our crew are operating together in space. We continue with several of the science activities that are focused on the crew health and life in space. So still a lot of things going on.
And 4 observers working under the psychological pressure of a historic mission may describe what they see with some subjectivity. Both of those things are true. But here is the problem with using them to dismiss what the crew reported. All 4 astronauts described the same anomalies independently and consistently, with real-time cross-verification between them. In the regions where the satellite data and the crew's observations already aligned, where the maps matched what they could see, there were 0 discrepancies reported. None. The inconsistency was not random. It was geographically specific, appearing in the same locations where the viewing angle differed most dramatically from what any satellite had ever used. That's not observer error. That's a pattern. Before the crew could dig further into what they were seeing, the signal died. 40 minutes of silence. As Orion passed behind the moon, its S-band and C-band antennas lost all contact with NASA's Deep Space Network. The receiving stations at Goldstone in California, Madrid in Spain, and Canberra in Australia. The moon itself, more than 3,400 kilometers in diameter, stood directly between Orion and every antenna on Earth. No signal could pass through that mass. There was no workaround. This was basic physics. The blackout lasted 40 minutes. The mission isn't over yet. We continue to learn from how our spacecraft and our crew are operating together in space. Several of the science activities that are focused on crew health and life in space are still underway. A lot of things still going on. During those 40 minutes, every scientific instrument humanity has ever built went completely blind to what was happening inside that capsule and on the surface below it. Let that settle for a moment. Not some instruments, all of them. The entire global infrastructure of human observation, Every antenna, every satellite, every telescope pointed at the moon saw nothing because the moon itself was in the way.
As part of the lunar flyby, the crew made their pass closest to the moon, flying at 3,138 miles per hour relative to the surface of the moon.
The Lunar Reconnaissance Orbiter was still running. Its cameras were still collecting data along its own orbit, unaffected by Orion's communication loss. In theory, it remained an independent source of observation throughout the blackout. But the LRO and Orion do not observe in the same way. And that difference matters more than it seems. The LRO was designed for one purpose: systematic global mapping. Its algorithms are built to normalize data, to remove variations caused by shifting lighting conditions so that the final maps reflect consistent surface properties, regardless of when a given image was. Consistency is what makes the data useful over time. But normalization has a cost. Subtle color variations that appear, specifically under low-angle light, exactly the conditions Orion was operating in, may be processed as noise. Not because they don't exist, but because they don't fit the model. The LRO isn't producing wrong data. It's producing accurate data for the purpose it was designed to serve. The problem is that the purpose of that system, and the question now being asked, are not the same thing. During those 40 minutes, the anomalies the crew had already reported didn't stop. They became more frequent, more defined. Color variations that had appeared occasionally during the first hours of the pass were now appearing at nearly every new region the crew turned toward, and there was no external system capable of confirming or contradicting any of it. No satellite, no ground station, no independent instrument of any kind. Just Wiseman, Glover, Koch, and Hansen. One spacecraft, and the surface of the moon scrolling beneath them in total silence. As part of the lunar flyby, the crew made their pass closest to the moon, flying at 3,138 miles per hour relative to the surface. They kept logging anyway, every observation timestamped, every coordinate recorded, every crew member cross-checking the others before anything went into the flight log. If they were going to be the only witnesses, they were going to be meticulous ones. When contact was restored, the crew began transmitting immediately. What they reported next hadn't been planned for either. 4 impacts and a gap no one knew existed. Wiseman saw it first. A single point of light against the gray surface, flaring and gone in less than a second. Before anyone could respond, a second flash appeared near the rim of a crater, sharp, unmistakable. Hansen called it out. Glover tried to estimate brightness. Koch logged the time and coordinates. Then 2 more followed during the blackout, witnessed only by the crew, with no external verification possible in that moment. 4 meteorite impacts within a single hour, directly observed by human witnesses on the far side of the moon, something that had never happened before in the history of spaceflight. Each one logged, each one captured by high-speed imaging systems aboard Orion. 4 independent events, independently verified between 4 crew members. The response in Houston was excitement, genuine excitement. This was rare data, but within that excitement, a technical question was forming that nobody had asked out loud yet, and when it got asked, the answer was not comfortable. The Lunar Reconnaissance Orbiter does monitor impacts, not through its primary camera, but through a data processing system that detects new craters by comparing images of the same region taken at different times. It has confirmed hundreds of new craters on the near side in recent years. Ground-based telescopes add to that by tracking impact flashes on the dark limb of the moon, where sunlight doesn't interfere. But the far side is never visible from Earth, and the LRO's comparison system runs on scheduled imaging cycles, not continuous real-time observation. During the 1-hour window when these 4 impacts occurred, there was no imaging pass scheduled over those exact regions. This is not a failure, it's a probability and coverage problem. But here's what it actually means. The entire global system for monitoring far-side impacts depends on the orbital schedule of one satellite. That schedule is not dense enough to capture short-duration events in narrow time windows. These 4 impacts weren't missed because they were too small. They were missed because nothing was looking at that exact spot at that exact moment. and nobody caught it for years, maybe decades. How many impacts have occurred on the far side since the LRO began operations without being captured by any instrument at all? That's not a hypothetical question. It directly affects the impact frequency models used to assess surface risk. The same models currently guiding the planning of Artemis III crewed landings near the lunar South Pole. If the data is incomplete there, where else is it incomplete? Light the satellites never captured. At 8:35 p.m. on April 6th, the sun disappeared behind the edge of the moon, as seen from Orion's windows. For nearly an hour, the crew witnessed a total solar eclipse that no one on Earth could see, an event visible only from their precise position in space. Glover described the solar corona expanding around the yellow-black disk of the moon. The corona, the outermost layer of the sun's atmosphere, normally hidden by the sun's overwhelming brightness, became visible as a faint halo stretching millions of kilometers into space. It will take scientists months to fully analyze what he captured, but the corona wasn't what stopped the crew cold. As totality continued, the lunar surface, which should have been completely dark without direct sunlight, became faintly visible. A second source of illumination was reaching it, Earthshine. Sunlight reflected from Earth's oceans and clouds and continents, traveling nearly 400,000 kilometers to land on the moon and bounce back toward Orion. Earthshine isn't new. You can see it from Earth on the dark side of a crescent moon, that faint glow that reveals the unlit portion of the lunar disk. Scientists have known about it for centuries. It's been measured, modeled, used as an indirect indicator of Earth's overall reflectivity. Nobody was surprised it existed. What nobody had documented was what it does to the lunar surface when you're 115 kilometers above it during a total eclipse, when it is the only light source hitting the ground, and 4 trained observers are watching in real time. The crew described a soft blue-white haze spreading across cratered terrain. Under Earthshine, the regolith showed subtle color variations completely absent from any existing spectral map. Not weak signals with uncertain interpretations, not anomalies that had been studied and set aside, absent entirely. The data set for this specific phenomenon didn't exist, because the conditions required to produce it had never been written into any observation plan. Here's why, and this part matters. Earthshine is roughly 10,000 times weaker than direct sunlight. The LRO's sensors are calibrated for direct solar illumination. Under Earthshine conditions, the reflected signal from the surface falls near or below the lower threshold of what those instruments are designed to capture meaningfully. During a total eclipse, when direct sunlight is completely blocked, Earthshine becomes the dominant illumination source, and that scenario doesn't appear anywhere in standard satellite observation plan. No instrument was ever designed to see the moon this way, not because it's impossible to design one, because this exact combination, the right position, the right timing, the right illumination, was never considered a priority. It existed outside the range of expected conditions, so it was never included, so it was never detected. Think about what we now had: silver ejecta and color gradients at Mare Orientale, green tones on the South Pole Aitken Basin floor, olive swirls across the Von Karman Highlands, a blue-white haze under Earthshine, 4 separate observations, 2 distinct lighting conditions, 0 matches in any existing data set, all missed for the same reason. The data loop. After Orion returned, scientific teams at Johnson Space Center and Goddard Space Flight Center began cross-referencing every crew observation against existing data. Every color description matched against LRO and Chang'e spectral surveys. Every coordinate checked against geological maps. The work took weeks, and here's what they found. In several cases, there were traces. Faint, inconsistent signals in older data sets that had been treated as background noise during normalization. Not because those signals were fabricated, not because anyone was careless, but because the algorithms that process satellite data are designed to filter out signals that are too weak or too inconsistent. The expected surface model. That's not negligence. That's how you build a globally consistent map. You smooth out the noise. You enforce consistency. You trust the model. The problem is what you lose when you do. Here's where it gets circular. The expected surface model was built from previous data. That previous data was processed using thresholds defined by earlier models. Those earlier models came from data collected even before that. The system refined itself over decades, becoming more consistent, more precise, more internally coherent. Each generation of data was compared to the generation before it and found to agree. That agreement looked like confirmation. It wasn't. It was the system talking to itself. We built a system that could only find what it already knew to look for. And for 53 years, nobody could stand outside that system and check. On Earth, this loop gets broken all the time. Field work, physical samples, independent instruments built by different teams with different assumptions. A scientist who walks into a place and sees something unexpected and immediately changes what they're measuring. That kind of external check is so fundamental to how science works that we rarely have to name it. On the moon, without a human presence, that check didn't exist. Every instrument calibrated against other instruments. Every model validated against models built from the same data. The entire lunar knowledge base, the maps, the spectral surveys, the impact models, the mineral distribution charts, was constructed inside a closed loop with no external reference point. Nobody designed it that way intentionally. Nobody made a decision to exclude verification. It happened because the moon is far away and humans hadn't gone back. That's it. That's the whole explanation. And it meant that for 53 years, the loop ran unchecked. Artemis II was the first time in 53 years that something arrived, which was not part of that loop, and the loop didn't hold. What comes next? The anomalies from Artemis II don't prove the moon is hiding something. There's no case being made here for structures or extraterrestrial activity. The explanation for the color discrepancies may turn out to be straightforward. Mineral interactions visible only at specific lighting angle, trace elements outside standard spectral detection ranges, optical effects that require a lateral viewing position to appear. That's entirely possible. But we don't know. And until 4 humans showed up with their eyes, we didn't know we didn't know. The 4 impacts missed by every instrument in our global network are not a scandal. They are a documented coverage gap, now confirmed for the first time. The Earthshine phenomenon revealing colors no satellite has recorded is not a conspiracy. It's a measurement boundary that was never noticed, because the conditions that expose it were never part of the observation plan. The silver ejecta, the green basin floor, the olive swirls, the blue-white haze, each may have a rational explanation waiting to be found. But finding those explanations will require updating models that currently have no room for them. Models that are being used right now, today, to plan Artemis III crewed landings near the lunar South Pole. Models that tell mission planners where it's safe to put boots on the ground. Models that were built by instruments never once tested against an independent observer at this range, under these conditions, over these regions. Now we know those models have gaps. Specific, documented, geographically confirmed gaps, recorded in flight logs, cross-verified by 4 crew members, and now sitting on the desks of analysts at Johnson Space Center, who are working backward through decades of archived data, looking for the signals that normalization quietly removed. The process of updating what we thought we knew about the moon has already begun. It will take years. Artemis II didn't expose a conspiracy. It exposed something more consequential, a verification problem that existed for 5 decades without anyone having the tools to find it. The map of the moon that we rely on is a map of the moon under conditions our instruments were built to measure. It was never a complete map. We just had no way to know that until someone showed up and looked from the outside. That distinction changes everything that comes next. What Artemis III is now looking for, what instruments future missions will need to carry, what questions are worth asking again, with human eyes rather than preset algorithms. The crew of Artemis II didn't just travel farther than any humans in history and come home with records to file. They stood outside a closed system for the first time in 53 years and saw something that system had been quietly missing the entire time. Something was detected during Artemis II. It shouldn't have been there, not according to the data we spent 53 years building and trusting. And the most important question is not what it was. The most important question is what else the data has been missing all along, quietly filtered out by systems that were never designed to detect their own limits and never had a reason to try. Will Artemis III go back to find out? That mission is already in planning. And the observation targets are being revised right now in light of what Artemis II reported. Subscribe and turn on notifications, because when those findings come in, this channel will be the first place to break them.